Equal to our last discussion on atomic theory and atomic structure, the link to that video will be displayed at the beginning of this video. In this lesson, we are going to look at quantum number and electronic configuration. There are two theories that will give us the basic foundation of what quantum number are about. And those theories, the postulate of Niels Bohr, that is Niels Bohr atomic theory, and the postulate of another scientist called Erwin Schrödinger. In atomic theory, Niels Bohr said that an atom is made up of a nucleus. The nucleus is located at the center of an atom, but electrons are located in only regions known as orbitals. Now, those orbitals have some amount of energy associated with them, and once electrons are located in their orbitals, they do not gain energy nor lose energy. Also, the scientist Schrödinger said that electrons behave like waves, and the position and properties of electrons in their orbitals can be ascertained by solutions which are called quantum numbers. So that is why we are discussing quantum numbers today. But before I go into quantum number, I want to bring into your notice of the work of a particular scientist known as de Broglie. So, de Broglie gave the wave particulate nature of electron. I'm bringing this up because Erwin Schrödinger said that electrons behave like waves. Other scientists said that electrons are matters. Okay, electrons, they are particles. But de Broglie had a different idea, and his own idea was that electron has a dual nature, which is called particulate wave nature of electron. That is, electron can behave both as a particle and as a wave. And he gave the formula for calculating the wavelength of electron. What he did was to combine the works of two scientists. He combined the work of Max Planck. According to Max Planck, the energy of a photon is given as Planck's constant multiplied by frequency. Then he also made use the work of Albert Einstein. According to Albert Einstein, the energy of a photon is equal to the product of mass and speed of light to the power of 2, E equals mc squared. So, de Broglie combined these two equations, and we have HF equals to mc squared. Remember that c is the velocity of a wave, and the velocity of a wave is equal to the product of frequency and wavelength. So if you make frequency subject of formula, frequency is going to be equal to c over lambda. So that means we can write our equation as hc over lambda equals to mc squared. Then 1c can cancel 1c. We are going to be left with h over lambda equals to mc. Then if you make lambda subject of formula, lambda over h will be equals to 1 over mc. Then if you multiply both sides by h, we have lambda equals to h over mc. So note that this is the equation for calculating the wavelength of electron when it behaves like a wave. So now let's go to the business of the day. We are dealing with quantum numbers, and we said that quantum numbers are solutions that are used to describe the position, the location of electrons in their orbital. Niels Bohr said that electrons are only located in regions known as orbitals. So if you want to locate electrons in their orbital, what we use to do that is quantum numbers. Now, there are about 4 sets of quantum numbers. Now, there are 4 quantum numbers that was given by Erwin Schrödinger. And there are 3 things I would like you to know about any quantum number that you pick. Number 1, I would like you to know what is used in representing that quantum number. What is the symbol of the quantum number? Number 2, I would like you to know what the quantum number actually does. What is the function of the quantum number? Number 3, and I would like you to know the range of the quantum number. Now, the first quantum number that we'll look at is called the principal quantum number. So, as I said, we'll look at the symbol, the function, and the range. How do you represent principal quantum number? So, the symbol for representing principal quantum number is lowercase n. So, when dealing with an atom, when you see n, this n represents principal quantum number. Now, what does principal quantum number do? Principal quantum number tells us the energy that is associated with a particular orbital. So, electrons are located in orbital. The energy of that orbital is given by the principal quantum number. Then again, principal quantum number distributes electrons into their shell, and this shell is also called energy level. We can also say that the principal quantum number tells us the distance of electron from the nucleus, and I'm going to explain what this means. But let me go to the range of the quantum number. Note that principal quantum number takes its range from n equal to 1 to 2 to 3 and so on. But personally, I believe that principal quantum number ranges from n equal to 1 to 7, at least for now. When we get to periodic table, you know why I said that principal quantum number ranges from 1 to 7. Alright, so now what does this really mean? As I said, principal quantum number distributes electron into their shell, and the common shell that we have are known as the K, L, M, N shell and so on. So if the principal quantum number of an electron or for an orbital is 1, that means that electron belongs to the first shell, which is called the K shell. If the principal quantum number is 2, it means it belongs to the L shell, and so on and so forth. So when we say that principal quantum number tells us the distance of an electron from the shell, it means that an electron that has a number of n to be equal to 1 is closer to the nucleus compared to an electron that has its principal quantum number to be 4. This value n can give us the total number of electrons that is located in the shell of an atom. What I mean is, the formula for calculating the total number of electrons in a particular shell is given as number of total electron is equal to 2n squared. This means that in the first shell, which is the K shell, since n is equal to 1, the total number of electrons that can be located in that shell will be 2 times 1 squared, which is 2. So your first shell can take only 2 electrons. Now, in the second shell, which is L shell, and your n is equal to, it means that the total number of electrons that they can have is 2 times 2 squared, which is 2 times 4, and that is 8. That is why we draw electronic configuration of, let's say, sodium, which has a total of 11 electrons. We draw it as the first shell, we put 2 electrons. Then the second shell, we put 8 electrons. That is 10. Then the last electron, we put it in the third shell. That is because the principal quantum number can give us the total number of electrons that is located in the shell or the energy level. So all these circles, they are the energy level of the shell. Now let's move to the second quantum number. The second quantum number that we introduce you to is known as the angular quantum number, which is also called subsidiary quantum number. So know that it is called angular or subsidiary, and some people also call it azimuthal quantum number. Now, I said that there are 3 things that we must say. The first one is the symbol. The symbol for azimuthal quantum number is lowercase l. Now, what does this quantum number do? What is the function? The function of angular quantum number is that it distributes electrons into their subshell, which is also commonly referred to as orbitals. So, while the principal quantum number distributes electrons into their shell, subsidiary quantum number or azimuthal quantum number, as the case may be, distribute electrons into their subshell. This quantum number can give us knowledge about the shape of the orbital. And the orbital that we are talking about here are the S, P, D, and F orbital, which you must be familiar with. Now, what is the range? The range of azimuthal quantum number L is, it ranges from 0 to n-1. Alright, so note that the range of azimuthal quantum number is 0 to n-1. This means that the first value that is available for azimuthal quantum number is 0. We must know the value of the principal quantum number of an electron before we can ascertain the value for the azimuthal quantum number, because the range is from 0 to n-1. What we are really saying then is that if the value of your principal quantum number is 1, the value of azimuthal quantum number then will be 0 to 1 minus 1, and 1 minus 1 is 0. So that means your L can only be 0. So it means that when n is equal to 1, then L can be only 0. Then if the value of the principal quantum number is 3, then the value of azimuthal quantum number can then be 0 to 3 minus 1, and 3 minus 1 is 2. So the value of L that is available when n is 3 will be 0, 1, and 2. That is how you get the range of azimuthal quantum number. Let me say emphatically that when your L is equal to 0, the orbital that is being described is s orbital. When your L is equal to 1, the orbital that is being described is p. When L is equal to 2, that is the d orbital. And lastly, when L is equal to 3, that is f orbital. So if you have an electron described by n is equal to 3, L is equal to 1, that means that this electron is located in the third shell, and in the third shell, the subshell or the orbital in which that electron is located is the p orbital. Because when L is 1, that means you have what? P orbital. Let's take another example. If the value of the principal quantum number of an electron is 1 and the L is 0, that means this electron is located in the first shell, so that will be 1, and the orbital or the subshell for that electron will be s, so it's located in the 1s orbital. Let me picture this to you so that you understand better. Let's say we have boron nucleus. Remember that boron has 5 electrons. So the first shell is going to take 2 electrons. So we have 2 electrons in the first shell. And the second shell will take 3 electrons. The second shell has 3 electrons. Now let's say we want to describe the position of this particular electron. Since this electron is located in the second shell, it means that the value of its principal quantum number will be 2. Right? It's located in the second shell. Then the value of its azimuthal quantum number, L, may be 0 or 1, depending on which subshell or which orbital is located particularly. We cannot know the subshell is located with this, but as we progress, we are going to know whether it's located in the s orbital or it's located in the p orbital, particularly when we get into electronic configuration. I just want to put in your mind what we mean by when n is equal to a particular value and when L is equal to a particular value. So that is the information that you should know about azimuthal quantum number. Now, before we move to the next quantum number, let's do a summary table of what azimuthal quantum number entails. So we said that azimuthal quantum number distributes electrons into their subshell or orbitals. So we can talk about the orbital of the electron. And we also say that it gives us the shape. So we can talk about the shape of that orbital. Then we can talk about the maximum electron capacity of that orbital. Then also we can talk about the degeneracy of that orbital. So if your azimuthal quantum number is 0, remember that it starts from 0. That means you are dealing with the s orbital. The shape of s orbital is spherical. That's a spherical shape. The maximum electron capacity is 2, and s orbital is a non-degenerate orbital. So I will explain what a non-degenerate orbital is. Remember that I said that the formula for calculating total electron in a shell, not subshell now, in a shell is equal to 2n squared. The way you are going to know the total electron, this is for a shell. The way you are going to know the total electron in a subshell is to use the formula 4L plus 2. This is for subshell or orbitals. Okay, so 4L plus 2. So if your L is equal to 0, that means we have 4 times 0 plus 2, which is equal to 2. When your L is equal to 1, so we have 4 times 1 plus 2, which is 4 plus 2, and that is 6. That is how you know the total electron in a particular subshell or the orbital. So let's continue with our summary table. When your azimuthal is 1, you know that we are dealing with the p orbital. The shape of p orbital is known as dumbbell. That's a dumbbell shape. The maximum electron capacity from what we calculate is 6. Then the degeneracy is 3. I'm going to explain degeneracy as we go forward. Now the next one is when your azimuthal has a value of 2, that is d orbital. The shape is double dumbbell. The maximum electron capacity is 10 and it has 5 degeneracy. Then the last one, when your L is 3, the orbital is F. It has a complex shape. I will stick with complex. The maximum electron capacity is 14 and degeneracy is 7. So this is how we are going to summarize azimuthal quantum number. Now it's time for us to go to the next quantum number. Let's see the next quantum number and what it really entails. The next quantum number that we should probably talk about is the magnetic quantum number. And then, as usual, let's begin with the symbol. So magnetic quantum number is symbolized with M, although in some textbook you can see it as ML, but I'm going to stick with M. Now, what does this quantum number do? Magnetic quantum number gives us the spatial orientation of orbiter. That is how these orbiters are oriented in space. Now, going to the range for magnetic quantum number is negative L to positive L, including 0. That is from negative L to 0 to positive L. This means that for us to know the value of magnetic quantum number, we must know the value of the azimuthal quantum number. And then, as you will see, for us to know the value of azimuthal quantum number, we must know the value of principal quantum number. So now let's take some example. Let's say that we have an electron that's located in the third shell, which means that its n is equal to 3, and then it's located in the second subshell, that is, its L is equal to 2. It means that the value of the magnetic quantum number that be available for this electron, the M is going to be -2, -1, 0, 1, and 2. So you take value from negative L to 0 to positive L. So if they give you a question like this, judge if the combination of the set of the following quantum number is correct. So we have n equal to 1, L equal to 0, M equal to -1. Secondly, let's say we have n equal to 3, L equal to 3, M equal to -3. Then number 3, let's say we have n equal to 4, L equal to 2, M equal to -3. And lastly, let's say we have n equal to 3, L equal to 1, M equal to 0. So we have to judge if these combinations of quantum number is correct. So let's start with the first one. If n is equal to 1, L can be equal to 0, but M cannot be equal to -1. It's not possible because your M takes reading from L. So if L is equal to 0, if the azimuthal quantum number is equal to 0, your M can only be equal to 0. It cannot be equal to -1. So this first one is wrong. Now the second one, if n is equal to 3, if the principal is equal to 3, the azimuthal cannot be equal to 3 because azimuthal take value from 0 to n-1. That is, your L can only be 0, 1, and 2. Cannot go beyond that. So this second one is also incorrect. Then for the next one, if your n is 4, certainly L can be equal to 2. Because if n is 4, your L can be 0, 1, 2, and 3. So this is correct. But what of M? If L is equal to 2, then M cannot be equal to -3. This is also incorrect. Then for the fourth one, if n is 3, L can be 1 because the possible value of L when n is 3 is 0, 1, 2. So L can be 1. And if L is 1, M can also be equal to 0 because when L is 1, M can be -1, 0, and 1. So this is going to be the only correct combination of quantum number. Now the last quantum number that we are going to talk about is the spin quantum number. So the symbol for spin quantum number is S. In some textbook you can see it as MS. So the function of spin quantum number is that it gives the direction of spin of electrons in their orbiter as either clockwise or anti-clockwise. Alright, this will make sense to you when we start electronic configuration. So those are the first set of quantum numbers that are used to give the location or the position of electron in the orbiters. Now let's talk about electronic configuration. We have said that quantum number describes the location of electrons in orbiter. Electronic configuration, on the other hand, gives the arrangement of electrons in their orbital. So it is not enough for us to know the location of electron. We need to know how they are arranged. Now, there are three principles that guides the arrangement of electron in atomic orbital. The first one is Aufbau's principle, which you should be familiar with. So what does Aufbau's principle says? Aufbau's principle says that in filling electrons in their orbital, orbitals of lower energy are filled before orbitals of higher energy, which means that electron goes into the orbitals in increasing order of energy of orbitals. So lower energy orbitals are filled first before orbitals of higher energy. That is Aufbau's principle. Then the second principle is known as Hund's rule. And Hund's rule applies to degenerate orbitals, which I'm going to talk about very soon. So Hund's rule says that electrons are filled singly into degenerate orbitals before pairing commences. Now, what does that mean? Electrons actually occurs in pair, whether bond pair or lone pair. Electrons go into their orbitals one by one, singly, before they start to pair. This will make sense to you very soon. Then the last one is known as Pauli exclusion principle. So Pauli exclusion principle can be stated in two ways. It can be stated as no two electrons can have the same spin. That is, no two electrons can spin in the same direction. The spin of electron must be parallel. Or you can say that no two electrons can have all the four sets of quantum numbers to be the same. What this is really saying in essence is that no two electrons can have the same value of all the four quantum numbers to be equal. If two electrons have their n to be the same, that is, both electrons are located in the first shell, then the two electrons are located in the s orbital, and the two electrons have the same orientation in space. Let's say they have m of 0. By the time they spin, they will either spin either clockwise, plus half, or the other spin anti-clockwise, negative half. In case I forgot to mention, the range of spin quantum number is either plus or negative half. That is, electron can either spin clockwise or anti-clockwise. Now let's add flesh to what we have been saying so far. Let's begin with Aufbau's principle. So Aufbau's principle says that orbitals of lower energy are filled first before orbitals of higher energy. So how do we know which one is higher energy orbital? Right? The way we ascertain the energy associated to an orbital is to use Aufbau's diagonal rule. And this is how it is drawn. So you have 1s, and the next thing is 2s, 2p. Note that 1p does not exist and 2d does not exist. I will explain why. Then the next thing we draw is 3s, 3p, 3d. There's no 3f. And the next one is 4s, 4p, 4d, 4f. The next one we should draw is 5s, 5p, 5d, 5f. All right, let's stop here, but you can continue to 6 and to 7. I said that 1p does not exist because if you have 1p, it means that this is 1. This is the value for principal quantum number. So principal quantum number n will be equal to 1. Then for p, the value of L when we have p orbital is also 1. And remember that when we have n is equal to 1, we can only have our L to be equal to 0. L cannot be equal to 1. That is why you cannot have 1p. Same thing, that's the same reason why you cannot have 2d, and same reason why you cannot have 3f. Because if you say 3f, it means that n is equal to 3 and L is also equal to 3, and that is not possible. Alright? So now that we have our diagram, then you place some arrows, and from this Aufbau diagram rule, we can ascertain the energy that is associated with each orbital. So what we'll do is to take the arrows, take it one from top, and move down the arrow. What I mean is, we'll start with this first arrow. So the orbital with the lowest energy will be 1s. To the second arrow, that will be 2s. Now we'll go to the third arrow, but we'll start counting from top. So the next one will be 2p. So the energy of 2s is lower than 2p, and we must move down the arrow. So the next one will be this one, 3s. Then we move to the next arrow, which is this arrow right here. That will be 3p. move it down. The next one will be 4s. Then we'll go to the next one, which is this one right here. That is 3d. Then take it down. Next one will be 4p. Then followed by 5s, and so on and so forth. So it means that when we are filling electrons into the orbital, we must fill in 1s before 2s, 2s before 2p, 2p before 3s, 3s before 3p, and so on and so forth. So that is what Aufbau principle is saying, that orbitals of lower energy are filled before orbitals of higher energy. This is what you must know as the energy associated with each orbital. With this information, you can take some practice example. Now let's find the electronic configuration for the following atom. Let's say we have oxygen. Let's look for that of neon. Let's look for phosphorus. Let's do for calcium. And we can also do for some ions. Let's do for magnesium ion. And let's do for chlorine ion. So starting with oxygen. Know that oxygen has 8 electrons. So we want to fill 8 electrons without 1s. The maximum electron capacity for S is 2. Don't forget. P is 6. D is 10. F is 14. You must have that handy. So we are filling 8 electrons. S can take maximum of 2. We are left with 6. The next one will be 2s. S can take 2. So that is 4. We are left with 4. Then the next orbital is P. P can take maximum of 6, but we are left with 4 electrons. So this will be 2p4. Now the way you confirm is what look like the exponent at the electron. When you sum up the electron, it must equal to the electrons that the atom have. So 2 plus 2 plus 4 is 8, and oxygen has 8 electrons. That is one way for us to check what we are doing. And then the arrangement of the orbitals must also be correct. Number 2, we have neon. So neon has 10 electrons. We are filling 10 electrons. Electronic configuration for neon is going to equal to 1s2, 2s2, that is 4. We are left with 6. So P can take up to 6, that would be 2p6. So this will be electronic configuration for neon. The next one is phosphorus. Phosphorus has 15 electrons. So we are going to have 1s2, 2s2, 2p6, that is 10. Then after 2p is 3s. S can take only 2. So that is 12. We are left with 3 because the total is 15. And that would be 3p3. This is the electronic configuration for chlorine. Then for calcium, calcium is 20. We have 1s2, 2s2, 2p6, that is 10. 3s2, that is 12. 3p6, that is 18. Then after 3p is 4s. So 4s2, that is 20. So this is going to be a configuration for calcium. Now, in your textbook, you can see calcium written this way. Ar4s2. That is because argon is a noble gas and argon has 18 electrons. So this is more or less like saying 18 electrons for the electronic configuration for argon, then plus 2, which is going to equal to 20. So at times, electronic configuration can be written in terms of noble gases, which means that we can equally write electronic configuration for phosphorus as neon, which is 10 already, then 3s2, 3p3. So when you see something like this, do not be confused. So this is the details about Aufbau's principle, and I will use it to write electronic configuration. Now let's talk a little bit about Hund's rule. Now let's give a little more details about Hund's rule. Remember that we said that Hund's rule said that electrons goes into their orbital singly before pairing commences. To explain Hund's rule, I will take electronic configuration for fluorine as a case study. So fluorine has 9 electrons. Its electronic configuration will be 1s2, 2s2, 2p5. Alright, 2 plus 2, 4, plus 5, 9. This is what Hund's rule is saying. This is one way, this 1s2, 2s2, 2p5 is one way of writing electronic configuration. But we can also write electronic configuration this way. So this is 1s orbital. This is 2s. This is going to be 2p. Remember I talked about degeneracy of orbital, and I said that s orbital does not have a degenerate orbital, p orbital has 3, d has 5, and f has 7. This is what we mean. If you take s orbital does not have suborbital, so it is not a degenerate orbital. But p orbital is degenerate. That is, it can be subdivided into 3. You can have px, py, pz. And then each of these suborbital can take 2 electrons. That is why your p orbital can take maximum of 6 electrons. Then your d orbital is a degenerate orbital also. It has 5 degeneracy. So 1, 2, 3, 4, 5. And 2 orbital can go into each suborbital. That is why this can take 10 electrons. Then lastly, your f orbital is also a degenerate orbital, and it has a degeneracy of 7. Alright, so that's what we mean by degenerate orbital. Now coming back to this, electronic configuration of fluorine can then be written this way. 2 electrons in the s orbital. You can see the way I'm writing the directions of those electrons is in opposite spin. So we must obey Pauli exclusion principle that says that 2 electrons cannot spin in the same direction. Then for the 2s orbital is like this. Now when we are filling a degenerate orbital, we are filling 5 electrons. So we must fill electron one by one. That's what we mean by singly. So we have filled 3 electrons. Now we can now begin to pair. So we have filled 3 electrons, remain 2. So we can put 1 here, we can put 1 here. That is what Hund's rule is saying. So if you have a degenerate orbital, let's say you want to fill electron into a p orbital, and you want to fill 3 electrons into this orbital, into this p orbital, it will be incorrect to write it this way. Right? This will be incorrect because filling must be done singly before you start pairing. That is Hund's rule. Then lastly, Pauli exclusion principle says that no 2 electrons can spin in the same direction. What it means is that when you have 2 electrons in an orbital, their spin must be opposite to each other. So you can write it this way, or you can write it this way. But it will be incorrect to write it this way. This will be incorrect. Then this will also be incorrect. They cannot spin in the same direction. That is Pauli exclusion principle. And that is all about electronic configuration. What I'm going to do for you is to take some practice question on writing electronic configuration and quantum numbers. So watch out for that in the incoming video.